Good day, sir. I'm Aider Sega from BSE Italy, and I will now discuss my answers on the lesson for ideal gases. So, problem number 71. Hydrogen at 400 degree Rankine occupies 30 cubic feet. A. Find if the volume is increased to 90 cubic feet at constant pressure. What is the final temperature in degree Kelvin and degree Celsius? If the pressure is tripled from the state 2 in A, while the volume remains constant, what is the temperature? And C, an ideal gas occupying 0.308 cubic feet expands from 100 pound per square inch to standard atmospheric pressure, while the temperature remains constant. What is the final volume? So this problem is an manifestation of Avogadro's law, where the pressure is directly proportional to the temperature. For solving A, so have to choose the Charles law, where the temperature and the volume is directly proportional. So in order to find for T2, we have the equation T2 is equal to T sub 1 times V sub 2 divided by V sub 1. So substituting all the given from the problem, so we have the value of T2, which is equal to 1200 degree Rankine. So in order to convert this into degrees Celsius, just have to minus it by 491.67 and multiply it by 5/9. So the T2 therefore is equal to 393.51 degrees Celsius. Now to find its temperature in degree Kelvin, we just have to add 273.15 from the previous solved temperature, which is in degrees Celsius. So the T2 therefore is equal to 666.66 degree Kelvin. Now for B, so we have to use the Avogadro's law in here, where the pressure and the temperature is directly proportional. So we have the equation, this equation. So in order to, we have to transform this equation in order to solve for T2 of if the pressure is tripled here. So we have to put 3 here since the pressure should be tripled. So we have now the formula for T2 is equal to 3 times P2 times V2 times T1 divided by P1 V1. So substituting all the given to the equation, we now have 3600 degree Rankine. So in order to convert it into degrees Celsius, we just have to again minus 3600 degree Rankine by 491.67 times 5/9. So the T2 therefore is equal to 1726.85 degrees Celsius. Now for the T2 in the degree Kelvin, we just have to again add 273.15 to the solved temperature in degrees Celsius. So the T2 therefore is equal to 2000 degree Kelvin. Now for the C, finding the final volume, so we have to use the Boyle's law here, where the pressure is inversely proportional to the volume. So for V2, we have equal to P1 V1 divided by P2. So for the P2, we have you just have to add the from the problem, it is given there that the it is given it is stated that the gas occupied or expands from 100 the gas expands from 100 pound per square inch to standard atmospheric pressure. So we have to add the atmospheric pressure from the initial pressure. So the P2 now therefore is equal to 114.7 pound per square inch. Now we just have to substitute it to the formula. So the final volume therefore is equal to 2.4 cubic feet. Next, the temperature of an ideal gas remains constant while the temperature changes from 14.7 pound per square inch to 100 pound per square inch. A, if V1 is equal to 3.2 cubic feet, what is V2? And B, if the mass of a gas is 0.2 pound, what is the change of density? So, in order to solve for A, so we have to use the Boyle's law. So we have V2 is equal to P1 V1 divided by P2. So substituting all the given from the problem, so the V2 therefore is equal to 0.41 cubic feet. So, oh by the way, this 114.7 pound per square inch is from this initial pressure, the 14.7 added to the final pressure, which is equal to 100 pound per square inch. Next is to compute for the change in density. So the change in density is equal to density 2 minus the density 1, which is also equal to the mass times 1 over V2 minus 1 over V1. Now we just have to substitute all the given to the formula, and the change of density therefore is equal to 0.425 pound per cubic feet. Next, an ideal gas is confined within an inflexible tank is 85.3 pound per square inch and 240 degree Fahrenheit. If the gas is cooled until P2 is equal to 25.3 pound per square inch, what will be the temperature in degree Rankine, in degree Fahrenheit, and in degree Celsius? While the pressure remains constant, remains constant at 90 pound per square inch, the temperature of an ideal gas changes from 100 degree Fahrenheit to 240 degree Fahrenheit. For an original volume of 18 cubic feet, what is the final volume? So in order to solve for A, so for the temperature, so we have to use the Avogadro's law here, where the temperature is directly proportional to the pressure. So for T2, we have T2 is equal to P2 times P1 divided by T1. So substituting all the given from the problem, we have T2 therefore is equal to 280 degree Rankine. So in order to convert this into degrees Celsius, just have to minus it by 491.67, then multiply it by 5/9. So temperature in degrees Celsius therefore is equal to negative 117.6 degrees Celsius. Now for the degree Fahrenheit, we just have to minus the previously solved temperature in degree Rankine by 460. Now the T2 is equal now to negative 180 degree Fahrenheit. And for the final volume, it is we will use here we will solve this using the Charles law, where the temperature and the volume is directly proportional. Now, formula for the final volume now is equal to V2 is equal to T2 times V1 divided by T1. Substituting all the given to the equation, we have the final volume therefore is equal to 21 cubic feet. Next, an engineer estimates for proper ventilation of an industrial plant 40,000 cubic feet per meter are needed when the atmosphere is at 100 degree Fahrenheit and 14.3 pound per square inch. What volume of air is measured under standard conditions of 60 degree Fahrenheit and 14.7 pound per square inch is being handled by the fans? So in order to solve for the volume of the air, we are going to use the Avogadro's law, where the pressure and temperature is directly proportional. So for the V2, we have the equation P1 times P1 times T2 divided by T2 times P2. So substituting all the given to the equation, we have the final, or the volume of the air is equal to 36,132.17 cubic feet per minute. Next is a gas has a density of 0.0892 pound per cubic feet at 14.7 pound per square inch and 32 degree Fahrenheit. So what is its specific volume at 150 pound per square inch and 100 degree Fahrenheit? Calculate its gas constant and molecular weight. Now the specific the given is the density of the gas. So in order to solve for its specific volume, so specific volume is equal to the reciprocal of the density. So since we have here the value of the gas density, so we just have to substitute it to the equation. So the specific volume therefore is equal to 11.21 cubic feet per pound. Now substituting it to the equation using the Avogadro's law and substituting all the given here. So the specific volume at 150 pound per square inch is therefore equal to 1.25 cubic feet per pound. Now for for the gas constant and the molecular weight, we have the formula R is equal to P1V1 divided by T equal to P2V2 divided by T. So we just have to use either any of these two, but I chose to use this R is equal to P2V2 divided by T2. Then I just have to substitute all the given in the formula. So the gas constant, the specific gas constant, therefore, is equal to 48.21 feet pound force over pound mass degree Rankine. Now for the molecular weight, we have to use the formula, we have to transform this formula, which is this specific gas constant equal to the universal gas constant divided by the molecular weight. So for the in order to solve for the molecular weight, we have to transform the formula into this one. Now substituting all the given to the formula. So the universal gas constant is equal to 1,545 feet pound force over pound mass degree Rankine. So dividing this one, we have the molecular weight of 32.5. Next, a tank 6-inch in diameter by 48-inch long contained acetylene at 250 pound per square inch and 80 degree Fahrenheit. After some was used, the acetylene was at 200 pound per square inch and 70 degree Fahrenheit. So A, what percentage of the contents of the tank was used? And B, what volume would the used acetylene occupy at 14.7 pound per square inch and 60 degree Fahrenheit? So the R for the acetylene in the in this specific weight here, we have R we have here 59.35 feet pound over pound degree Rankine. Here, the volume, we have to first solve for the volume of the tank. So the formula for the volume of the tank is equal to pi d squared, or the diameter, times inch squared divided by 4 times the height, and multiplied, and in order to convert these inches into cubic feet, I multiplied it by 1 cubic feet over the cube of 12 and cubic inch. So this will be cancelled and the remaining unit would be cubic feet. So the volume therefore is equal to 0.7854 cubic feet. Now we're going to use, in order to solve for A, we're going to use the Avogadro's law here, which is PV equal to mRT, and transforming the equation in order to solve for the mass, we have M is equal to PV divided by RT. So for the mass one, have P, or the density of the first density divided by volume divided by the specific gas constant times the temperature. So substituting all the given to the equation, we have the value of the mass 1, which is equal to 0.8822 pounds. Now for the mass 2, we just have to follow the same equation, but of course using the density 2 and the second temperature of the mass. So the mass 2 therefore is equal to 0.7191 pounds. And for the mass 3, just have to minus the mass 1 by the mass 2. So the mass 3 therefore is equal to 0.1631 pounds. Now for the percent of the acetylene used, we just have to divide the mass 3 over the mass 1. And performing the operation, we have 0.1849 or 18.5%. Next, for letter B, if T3 is equal to 60 degrees Fahrenheit and the pressure is equal to 14.7 pound per square inch. Now, again, using the Avogadro's law, we have for the volume 3 is equal to M3R times T3 divided by the pressure 3. Now, substituting all the given to the equation, we have now the volume of 2.38 cubic feet. Next is, during the process of 4 pounds of air, the temperature increases from 40 degrees Fahrenheit to 340 degrees Fahrenheit. Find A, the change, the delta U, or the change in the internal heat, and B, or the delta H, or the change in, the enthalpy. Now, for the temperature 1, in order to convert 40 degree Fahrenheit to degree Rankine, just have to add 460. 40 plus 460 is equal to 500 degree Rankine, and for the temperature 2, we have 340 degree Fahrenheit plus 460 is equal to 800 degree Rankine. Now to solve for the delta U, or the change in the internal heat, we have the formula delta U is equal to mCv times the T1 minus T2, or the mass times the specific heat times the delta T. Now the specific heat of air from the table is equal to, here have to Cv. This is 0.1714 BTU per pound degree Rankine. So we have here. And substituting all the given to the equation, we have the delta U is equal to 205.6 BTU. So BTU, since this unit will be cancelled as well as this one, so only the unit of BTU will be left. Now for the enthalpy, we have the formula M times Cp times T1 minus T2. Now, the Cp for, or the specific heat of air, have here is equal to 0.24 BTU per pound degree Rankine. Now substituting all the given to the formula, we have the enthalpy therefore is equal to 288 BTU.